Okay, so we brought in our boundary. We created a grid that was vector. We transformed that vector grid to a raster grid and cropped to the field. So now we're getting ready to do IDW. So there are a couple ways of doing, or maybe more than a couple ways of doing IDW in R. I want to show you one of them. So you can come back, it can come down to this chunk below here. You can use the assignment symbol. We're going to use a function called Gstat. So this function here is a very flexible function that it kind of knows what type of, between IDW and Kriging, it kind of knows what you're trying to do depending on what arguments you give it. So what we're going to give it is basically first a formula. So it has an argument called formula. And the formula we're given is just yield underscore pound per acre. So this is not a data set yet, it's just a column in the data, tilde 1. So this is how that we're telling it that we want to interpolate yield, the variable yield in pounds per acre. This name could be any other name in that data set, but that's what we want to interpolate here. And then of course we give comma, and we need to tell it what is the data that this column is in. So the data is called yield 17 underscore C, is the one that we import in the beginning of the script. If we run Gstat with only these two arguments, it will do IDW for us. It has another argument here, I believe is, let's see, maybe weights. I don't remember exactly, maybe variance. It has another argument that if you want to do Kriging, for example, you would have to calculate another step and then give that step to this extra argument that perhaps is variance. Because we're not doing that, it understands that we want to do IDW. So we can just run that. So if you run this, you create this object called IDW mod.
So what's this one?
The one is just the way that you specify that you want to interpolate for yield. So I mean, the function Gstat takes a formula, right? So there is a type of Kriging, for example, that you could have on this side another variable name. So you could have something else, let's say speed. But we're not going to do that. We're not going to get into that conversation because it gets a little bit more complicated than what I want to go. But here's basically, we're just saying interpolate over yield, and you still have to give it a formula. So that's why we use the tilde notation, and the one is just to say yield is what we're looking after. We don't want to relate it to anything else. Okay, so if you run IDW mod and you print it, so this is basically just setting the formula, and it's telling us that it has a dimension of 27,000 rows, and the data has 5 columns. If we check the class of this object that we created, is a class Gstat or list. So what happens is we use the Gstat function basically to set up the algorithm and to say this is the variable that we want to interpolate. It's coming from this data, but the interpolation has not happened at this step yet. So what we're going to do now is, if you come on the next chunk called IDWPred, that's where we're actually going to apply the interpolation to the data that we set up using a Gstat function. So in IDWPred, you can just give the assignment symbol. We're going to use a function called predict. So what we're doing is the first argument, we give the model that we set up above. So that's the IDW underscore mod. And again, as I was telling you, for any interpolation that you ever do, even if you're not seeing it, it is doing and running a grid behind the scenes. In our case, we did that ourselves. And the grid so the next argument here that we need to give it is the grid that has the setup of where we want to interpolate things over. And then we give that in the second argument so that we just say grid underscore R. Remember to give the raster version of the grid, not the vector, because that makes a difference here. So if you run this, it may take a moment because it's actually doing the interpolation for us. And whenever it's ready, it's gonna, it's just gonna have a solid text there. If we print now IDWPred, It is still a stars object. And now it has two new columns that, again, it's not very friendly to see the columns as we would with an SF object. This is a stars object, but it noticed two things. So it has two new columns that is giving us the summary for in this new object that we created. One is called Var1 Pred. One is called Var1 VAR. This is how it names, regardless of which variable you set up. So we asked to do interpolation on yield. Regardless of this name of this variable here, it will always return you these two columns. So Var1 Pred is basically the predicted values for each one of the cells of the raster that we gave it. And it's just giving us here a summary of the interpolated values. So not the data points that we gave it initially, but the interpolated values. They're ranging from 311 to 1958. It has 24,000 NAs. And maybe here's a good question, a good point for me to ask someone. Let's see, maybe someone that I haven't asked, maybe David. Why do you think that we have about like 2,400 NAs when our EO data actually didn't have any NAs? This is the interpolated values, right?
Use the data from our yield data to create the data, predicted.
So let me come back to this, and maybe this would help you. So right now, what the object, we haven't plotted yet, right? So the object that we created here, we're not plotting yet, so we're not seeing it. But why would we have on the interpolated grid, which is, I mean, on the grid that we use for interpolation, which we can kind of see here, why would we have, over 2,000 NAs when our original yield data had none? Anyone else can help David?
It can be the buffer if there is no point of the
So
beside the boundary.
you're kind of going the right direction, but so Sunday said that maybe it's because of the buffer that we don't have any data points there. It's not exactly that, but is it going that direction? Yes, Dennis.
Yes, I think it is making the interpolation of the whole box, including the outer part of the map.
Yes, you got it. So what Dennis was saying is that we have now NAs on the interpolated map because of all these gray cells that we clipped, right? So when we clip the raster to contain only the boundary, then we're only interpolating with inside the boundary. Anything outside the boundary is NA. So it doesn't interpolate over NA values, right? And again, this is happening because we could have skipped cropping the raster to the boundary, which then it would have created interpolated values all around this box here. But again, doesn't make sense, right? We're not interested in knowing what the next field over is because we don't even have points there. It makes no sense. It may be a road, maybe a creek, I don't know. Makes no sense, right? So we have on the interpolated map all the NAs because it's just the cells that are outside of the boundary, but it's still inside the bounding box of the raster. Okay, and then another point I want to make here. So again, IDW gives us an interpolated prediction. That's what the Var1 Pred column is. It also gave us a Var1 VAR column. So this column here contains all NAs. So all cells are NAs. And the reason is because we use IDW. If we would have used Kriging, as we were talking about earlier, Kriging produces for you an interpolation. So we would have all as well the Var1 Pred column, but also produces you a error or maybe variance map to go with it. If we had used Kriging here, then this Var1 VAR column would have been filled with values as well. Those values would not be interpolated values, but they would actually be the error of those interpolated values for us to see an error map. And then as we were talking earlier, Emma, if we wanted to see what parts of the field we have large error, we could go back, resample, bring those samples in, and then reduce the error on those areas. So this Var1 VAR column here, again, is all NAs because we're using IDW. If we had used Kriging, this would have been values that we could map and see which parts of the field are more variable with the prediction that's being done with interpolation, and then do something about it if we wanted.
We have NAs on the var1 predict. Yeah. So that's the interface inside the map, like the
So-
NAs on that column.
Yeah, so what the NAs on Var1 Pred are just the gray cells here, which are the points outside the boundary. Because when we crop the raster using the boundary, is basically saying everything inside the boundary, keep it, everything outside of it set as NA. So we don't interpolate over those points. Yeah, so that's why we have those. If we were to count how many cells we have outside of the boundary here, that would be the same as the number of NAs in this column.
So how is it different from the var1 VAR?
So Var1 VAR, it's not given to us here because we're using IDW. If we were using Kriging, Var1 VAR would have values, and it would have the same number of NAs as Var1 Pred actually, because it would have error values within the boundary still. So we would have values here that would be related to the error of the prediction instead of the prediction itself. The prediction itself is Var1 Pred. Var1 VAR is the variability or the error around that prediction, which again, IDW does not give us. Kriging does. Okay, so the next thing I want to do.
var1
Okay, Griffin, can you repeat that point again? Like Var1.
Sorry, can you
Yeah, could you repeat your last point? Like Kriging would have given us the values of errors, Var1 VAR. Could you repeat that point?
That's right, yeah. So Kriging, the way that Kriging works and the way that it actually calculates the interpolated values, it's able to give us an error map. So what an error map, so again, we don't have here because IDW does not do that, only Kriging does. But what the error map would be is just a map of the error of the predictions, right? So Var1 Pred is basically the values of the predictions themselves. Var1 VAR would be the error or the variance or variability around those predictions. So if we had done Kriging, we would have values here for the Var1 VAR as well, and we could plot them and see in the map where error is larger or smaller. And we can then make a decision if we think that, you know, if there is a part of the field that there were very few points, but we're still interpolating over that, that's probably going to be an area that's going to have larger error of the prediction. So what we can do then is if we want, we can go back to that field, take more samples. I mean, in this case here with EO data is not really doable, right? But let's say if it were soil data that you're taking soil samples, you could decide to go back to the field, pull out more samples in the parts of the field that have a large error when you interpolate, and then bring those data back, append them to the data, and then reinterpolate. That way you're basically providing more data in the parts of the field that have large error, and that will reduce the error of the interpolation. Again, we're not going to be seeing that here, but I just wanted to tell you what Var1 VAR is and why we have all NAs in this case. It's because we're using IDW, which does not calculate that for us. All right, so let's keep going here. The next thing I want to do is, so now we do have already, yeah, sorry, Dennis, or sorry, Peter, go ahead.
So for var1 VAR, does it mean this NAs because for IDW we don't calculate it?
Right.
It's everything.
Yeah, so Peter's question is if it's an A because IDW doesn't calculate it. Yes, that's exactly right. So it's fun. So because it's probably just a design option really from the people that developed the package, right? Because this function here, Gstat, if we wanted to do Kriging, we would have to do an extra step before getting to this function, and then just give the result of that previous step as an argument here. And in that case, the same Gstat and predict function would be used for Kriging as well. And then if it is Kriging, and the function knows because you would be given an extra argument, you would have given us a Var1 VAR. So because you use the same function to do both algorithms, it kind of gives you the same output. It's just that if it is IDW, then the output of var1 var is empty because IDW does not calculate that for you. And if it is kriging, then that has actual values that you can plot and analyze. Does that clarify? Okay, any more questions about this before we actually plot? All right, I don't hear anything, so let's keep going. So if you come here on the next chunk, our goal now is to plot the predictions of the interpolated predictions that we made above. So I left you the ggplot there, add a plus. We're not going to give any data set at this level of the ggplot. We're going to give at the individual geoms. So go ahead and type geom underscore stars. So the first thing I want to do is plot the IDWPred, which again is a stars object. So we say data equals IDW underscore pred. Let's just go ahead and run this for now and see what happens. So a couple of things that we can notice here, right? So we see that, so we have the predictions within the boundary, even though the field looks weird the way it is right now, but you can still see that it is our field. And we see that we only have interpolated predictions within the boundary. So when we were seeing all those NAs before is because those are all the gray cells here are all NAs. And again, that's happening because we're cropped to the boundary of the field. For some reason, and I don't really know if this is on purpose or maybe what happened. So the same author of SF is also the author of stars, right? And for some reason, when we plot a geom_SF object, so a vector file, it already sets the map in the right coordinates or in the right ranges of X and Y values. So it looks like the actual field when you're looking at the map. Well, on a geom stars, it doesn't do that by default. I'm not sure why, but it's just a weird thing that I wish it would have done. So let's make a few changes here on this map. So the first thing I want to do is change the color scheme. So to do that, we add the plus. I want to use scale underscore fill underscore Var1 B for bins. We can just run that and see. I want to show you another thing here as well. So Var1 B basically creates bins of the variables of the variable values and just uses those bins. There is also a different option here that is Var1 C, and that is for a continuous scale. So if we change that to Var1 C, we see now that this color scale is continuous instead of in bins and is perhaps a little bit, more complete with what we can see on the map. Okay, so let's add a plus here. The next thing I want to do is add the boundary of the field. So to do that, we're going to use geom underscore SF. Remember, IDWPred is a stars object, is a raster object. That's why we're using geom stars. The boundary is a vector file, so we use SF because it is an SF object. So we say data equals boundary underscore W. I want to say fill equals NA, so we don't, we can see through it. If you run that, now look what happened. When we added the SF object, again, geom SF knows that this is a map, and then it sets up the X and Y range of values to be what we actually would see in the map, whereas geom stars doesn't. So that happened because we use added geom SF. So again, here we're seeing our field, we see the boundary, we see the interpolated values, all that. Another thing I want to do here is, even though, I guess you can kind of see, like if you look closely, you do see now that we have cells, right? I think that's kind of clear, especially if you look at some of the yellow ones that are very easy to see the cells. So these are the cells that we produced on the grid, right? These are not data points. It's not a point anymore, right? So before the EO was a point, now it's a continuous raster where each cell has a value. And we basically filled in all the gaps. So if you remember, let me see, where was that? If we just go back, even to this plot here, we can see that. So we had a gap right there. We had a gap from the field to the boundary. All those gaps now have been filled in by the interpolation method. So now we have no gaps anymore, right? At least not inside of the boundary. Of course, we have the gaps for NAs outside the boundary, but that's something we decided by design. The last thing I want to add to this map is just add a plus, hit return. I want to bring in the grid vector so we can see the grid cells matching with interpolated values. So because I'm bringing the grid vector, we're using geom sf, right? So we say data equals grid underscore v. I want to change a few things here before we plot. So I want to change alpha transparency to 0.5. I want to add comma and say fill equals NA. Add comma and say size equals 0.1. So that's, just to help us to visualize it. If we run it, we can kind of see now the original vector grid. So the vector grid had not been clipped to the field at that point, if you recall. We did that on the raster grid. But I can kind of see how the cells of the grid are actually matching with how the values were interpolated. Something I want to do on my side, you don't have to do on yours because I don't want you to get things out of match with what we do in class, is if I had come here and let's say I used a grid of 100, how would that look like and how would that change the final map? So I just want to do that quickly here, this exercise. So you have to change the cell size both when you're creating the vector and also when you're rasterizing it. And I think we saw how this, or maybe now it's going to be even a little bit easier to see the blocks that we have in this field with a larger cell size. So I'm going to do the interpolation again, the prediction again, and I want to plot it again so we can see. So this is how the field would look like if we had used a 100 by 100 meter cell size. Okay, I will go ahead and undo everything I just did because I just wanted to show you kind of on the fly how the cell size plays a role on the interpolation. But for this class, we're using 10 by 10. The smaller is the cell size, the more details you'll be able to see. Yeah. Of course, again, the decision of cell size should be driven by other things, right? I mean, it should be based on how many data points you have. It should be based also on if the cell size even makes sense from a application standpoint, right? So let's say if we did a 1 by 1 meter cell size, it would be even finer than this. But I mean, which grower is going to be able to manage on a meter by meter basis? Probably not very applicable in that sense, right? So we do want to find a value that makes sense with the data, but it's also applicable in reality to whatever that's going to be used for when it derives some type of management decision. Okay, so there's the next step that I want to do here is the following. I heard or I read somewhere saying that there are people that work with rasters and there are people that transform rasters to vector and work with vectors. What I want to show you is the second option. And the reason for that is because from a learning perspective, I think it's easier to see a vector file in R as we're using SF than it is to see a raster file that is using stars. It's just from the visualization standpoint and looking at the data, we're going to be working with vectors. So we're basically, so here's, just to walk you through again what we did, right? So we brought in the boundary as a vector. We created a grid as a vector. We transformed the grid to raster. We interpolated with the raster because interpolation only works with raster. And now the last thing is I want to transform this interpolated raster into a vector again. Bring that as vector again. That's what we're going to be doing here in this last part of the code. So I left you the object that we're naming it. So IDWPred v for vector. We're going to start with our interpolated IDW object, which is called IDWPred. Add a pipe to transform. So right now, IDWPred is a stars object, right? So if we just print that, it is a stars object. To transform that into a SF object or going from raster to vector, we use again the function called st_s_sf. We do have to provide a few modifications to the arguments here. So one of them is we need to say it has an argument called s points that by default is set to true. I want to change this to false. And then it has another argument called merge that is its default is set to true. I also want to set it to false. So if you run this and you print that object, now it is an SF object that, and something interesting to notice here. Again, on a raster object does not have empty spaces. If you do want an empty space, that cell is still going to be there. It's just going to be coded as an A. A vector file, which is what we just transformed this into, can have empty spaces, right? So if you see now this object that we created, IDWPred V, it has 4,032 rows. This was the number of rows that we had on the raster that actually had data points, but we had a total of 6,000 rows on the raster because the extra 2,000 were NAs. Now, because we transformed from raster to vector, those NAs basically were left behind. And so we don't have any more NAs here.
Say as a point false.
We say as points equal false and merge equals false. Yep. Oh, sorry, merge equals false. I had true. Yeah, sorry. So you want both of them to be false. So what we see now in this vector SF object is we have two columns, right? So one is, or three columns actually. One is called Var1 Pred, which is our actual interpolated predictions. We have Var1 VAR, which is all NAs, again, because IDW does not give us a measure of the error of the interpolation. And then we have the geometry, which is basically now, so before we had a raster pixel, right? You can think of a pixel when we talk about raster. So if you take a photo with your phone, that has pixels, right? If you zoom in enough, you would start seeing pixels. That's what a raster is. A photo on a phone is a picture on the phone is a raster. Now, because we transformed from raster to vector, we don't have pixels anymore. We have polygons. So each cell that was a pixel before now is a small polygon. They're all connected because they're in a grid. So that's the reason why we have a polygon SF object when we transform. So the last thing I want to do is just a quick wrangling on the go here. So add a pipe. I just want to basically select and rename a variable. So to do that, we're going to use the function select that comes from the package dplyr. So you know that you should be calling the package directly, especially this exercise may be one where this would cause issues because I think the stars package may have a select function, but anyways. So I want to select the var1 .pred. Basically, I want to leave behind the var1 var because it has all NA, so it's not a really useful variable. So select lets us select a variable, but also allows us to rename that variable on the same function call. So what I want to do is call this IP for interpolated yield underscore pump breaker. Right, so this is the name I'm giving it, IP yield underscore pump breaker, just so we know that whenever we use this object, we'll look at this name, we know that this is not the original yield data, but it's actually interpolated yield data for this variable. And we also know what unit that's in, so pump breaker. So if you do that and you print it, basically that's what we end up with, the same number of rows as we had with near 4,000. And again, this is interpolated data. It's not our point data anymore. And then we have our geometries as polygons because those are all now small polygons rather than pixels. And lastly, it's always good. So, again, one thing that or really any programming language lacks when compared to an actual point-and-click software is that if you're using ArcGIS or something like that, you always have the map right in front of you, even though you may be doing things on the side. In R, it's not that way. So every time that we do something new, I like to plot that so we see the result of what we did. So the next thing here, let's just basically do a plot, right? So let's start with a ggplot, add a plus. We're going to call geom underscore SF. I want to bring here this new file that we created, right? So IDWPred V. So again, we're using GeoMSF because this is a vector file that we transformed in the step above. I want to add comma, and I want to, well, before, let me just do this. Let me just do it like that, so we can see, right? So right now is basically, it still looks like a grid, even though now it's not a pixel anymore. It's a small polygon. Each one of the cells is a small polygon. And I want to color these polygons according to the interpolated values of yield that we just did on the steps above. So to do that, we would add a comma, add the AES function, and say fill equals to, I just want to print this up just so we see again, the IP yield underscore pounds per acre. I get outside of the AES, add a comma, and I just want to say color equals NA. So whenever we have a shape, like whenever we have a polygon shape, fill is referring to the color inside, right, of that shape, and color is referring to the color of the outline of the shape. So I just want to say color NA. So we don't have a black line around each one of the polygons. I think that helps with visualization. And then lastly, I just want to change again this to a colorblind safe scale of color. So we do that by saying scale underscore fill, because we're changing the fill Var1, and we can use this Var1 C for continuous. If we run that, this is what you should end up with. Okay, so again, this is our wrangled, clean, interpolated vector yield data for 2017. So we did all that to get to this point. And this is one of the layers that we're going to be using moving forward in the class. And you're basically going to ask you to basically do everything we did today, but with the other data sets that you produced during the last assignment as well. Okay, so one thing I want to check here is, so we can see now the distribution of the interpolated yield values in space, but I want to see the distribution using a density plot, as we've been doing in the past, which is kind of like a histogram, if you recall. So we can just start with the IDW_pred_V is our data set. We plug that using a pipe into a ggplot, where inside ggplot we use the AES function to set the X to be equals the IP yield underscore pounds per acre. And then you get outside the ggplot, add a plus, hit return, and add a geom density. So again, this is just showing us the statistical distribution of this data. Right, so I just want to leave it here for a little bit so you can see this. If you remember, and this is a really important point to think of, is if you remember the distribution of this data here, when we were doing that for the point data, right? I'll be with you in a sec. For the point data, before we interpolated, it still had a tail, a little bit of a tail here on the lower side, right? So it still had some values that were higher here. Now, after interpolating, we're basically using that data, but now to interpolating to new cells and new values, right? So the original values of the yield contributed to the interpolated values, but the original ones are not here anymore. This is interpolated data now at this point, right? So that's why if you were to do the same plot for the original yield 17 clean and use the yield pounds per acre here, that would look different. Basically, well, you know what? Let me do something on the fly here, see if we can do that. I think that was yield 17 clean that we brought in the beginning. And I just want to say yes, X equals yield pound per acre. And I just want to give it a different fill. So let's say for a different color. Let's say blue. Okay, here we go. So in blue is the distribution of the original wrangled clean data. And in black is the distribution of the interpolated data. We see that they're different, right? Just to recap, they're not, the interpolated version used the original data, but it's not the original data anymore. Now it's interpolated. So that's why we see this difference here. Tyler, you had a question?
I just was gonna ask if you could scroll over here so I can get.
Oh, yeah.
I got it.
Okay, awesome. All right. So lastly, what we're gonna do is, because we will be using this layer again in a future lab, probably this Friday, I do want to export what we just created. I want to save that to file, right? So I want to save the IDWPred V into our data folders. So if you come here on the last chunk that is called exporting, we're going to use the function.
Can you go back up for one more second? I didn't get the new blue line.
Yes.
Thank you so much. Give me 1 second. You're good. We're good here in Tifton.
Okay, awesome. Thanks, guys. All right, I'm gonna go to the last chunk here. So again, we're going to export this interpolated map to file. To do that, we're gonna, because it is, again, I always say this just to remind you, it is an SF object, so we're gonna be using Writeisf because of that. So Writeisf, first thing we give it is the object that we want to, let me just give some returns here. The object that we want to save to file, which is the IDWPred V. You can add a comma, hit return a couple times just to break the code. The next thing we give it is a location and the name of the file. So I want to say .. to get outside the code folder, go inside the data folder, and I want to call this yield 17 _ interpolated. So this is the name of the file, and as you know, this is where we also give the extension of the file that we want to save as. This would be a .geo.json. And again, I'm going to say this, as every time you use Writeisf, make sure you change the argument called delete _ DSN to be true. The default is false. I want this to be true. So it always overwrites instead of append if you happen to run the same piece of code twice. So if you do that and you come on your files tab and you go on the data folder, you should see now it EO17 interpolated. Okay, so a couple of points I want to make here before I open for questions. As you're realizing, and I really want to stress this point for the upcoming homeworks as well, as you're noticing, we basically did, we started with one script that was used for wrangling. We brought raw data, we wrangled it, exported the wrangled version. And then we had another script that we imported the wrangled version, we cleaned it with the old editor, exported the clean version. Then we had a third script that we brought in the clean version, interpolated and exported the interpolated version. And then we're going to have another scripts coming next. They're going to be using data comes in, we do something, data goes out, right? So it's a way that we avoid having one very large script that contains everything. We could have done everything we did up until today in one script, but that just becomes so complicated, so cluttered, that is difficult to manage. So the idea here, and I really want to stress this for the class for sure, but also for your careers. Like as you start, if you do end up in a place where you do lots of data analysis, it's better to chop things into pieces that make sense and import, do something, export, than having one very long script that does all of it at the same time, but then it's just difficult to manage at the end of the day. I mean, I have some scripts that are like 3,000 rows of lines of code, which is something it's a lot of code and it's easy to get lost. So by chopping the activities into different scripts, that kind of helps to manage that. Okay, any questions about what we did today? So I didn't write yet the assignment, the next assignment, which is basically going to be asking for you to do what we did today with the other clean versions that you produced on the previous assignment. And as you know, the downside of that is you're going to have to do that before our class on Friday, because we're going to use them on Friday. So I will give that assignment as soon as I get out of class. I will write it and send it to you, but just so you already know, what I will ask you and what I do expect you to do is you would come, let me just show you what I would do on my side. You would come on your files on your computer on this project, you would go on code. You would basically, so the code that we did today was interpolation, right? You would basically copy this and paste 2 times, where one you rename to yield 19, the other you rename to yield 20. And then you basically individually on those scripts, you just added each one of the files that you created previously on the previous assignment. If your data, so I did share with you the key of the answers that I was looking for from the previous assignment. If your answers did not match with mine, go ahead, try to see what happened, try to see like what maybe was different in your code. Because again, if you start with the same code and same data, you should get to the same result. If it didn't get to the same results, probably something on the code happened. Maybe you had a different quantile selected than what we did in class. Maybe it's something else. Please go ahead and check. If you're still not able to produce the same summary as I did, let me know. I'll be glad to help you figure out what happened. But I do want you to go into the assignment that's going to start today with the right data. And again, you're producing the right data. I'm not sending you the right data. So make sure that we have all that covered. Okay, any questions?
Yeah.
Okay.
So while creating QMD, so are we always supposed to like copy and paste the QMD file, or can separate the QMD file from R or?
Yeah, so Sandesh's question was if you should always like copy and basically duplicate the QMD files, or if you can start one from zero. You can definitely start one from zero. And yeah, and I guess that's a good point, because I don't think I've asked you to create a QMD yet, right? It's really very simple, right? So you just come on this plus sign. This is where you would go if you want to create an R script, which is the type of script we used in the first class, or a R markdown, which we use in one of the initial classes too, or a Quarto document. So just click Quarto document. That's going to pop up some options. You just give it a title. I'm going to leave as entitled.
But the problem is like I don't have that option.
You don't have, okay, I can help you out. Well, I mean, if you don't have that option, then it's probably best if you just copy and paste a previous file. But if you wanted to create one, let's say for a different project, right, something not related to class, that's how you would do. Something I just wanna caution, if any of you ever do that, create your own Quarto files. So Quarto, I mean, this option, it has been there all the time to choose between source or visual. I tend to choose the source tab. The visual basically shows you more similarly to how it would show on the HTML. It is a little bit more friendly, I guess. So you see, like, instead of having the hashtags define headings is just already appearing like that. It's more friendly in the sense that let's say if you want to add a emoji, or if you want to add a picture or a table, you can just come here and add / like, so outside of a chunk. If you are on Quarto on the visual view, you can just add a / and it'll gives you options for adding things. So let's say if I wanted to add a figure to this file, I could click here. I can give where the file is on my computer or maybe on the internet, and I would say okay, and it would create for me that. You can also do this on the source side. It's just that on the source you have to know how to do that using code instead of just pointing clicking. So I guess in summary is we have not used the visual option yet. And that is the default option on the YAML part of the script when you create a Quarto. I just normally delete this and change to source, and that's how I work. You're free to do whatever you want if you want to use this, but I just wanted to caution you of that part of it. And of course, you have to save this, right? So when you open it as just untitled, you need to save it to somewhere, normally in your code folder. You still have to do that part. Okay, I'm just not gonna say this, 'cause I was just demonstrating. Any other questions?
GitHub, you have to open.
Oh, yeah. Thanks, Arminder. I always forget about this. Yep. So let's get attendance. I'm gonna create. Create that on GitHub right now. All right, so I just created on GitHub. Make sure you respond before the class ends today. If I open the issue during class, I will not take answers after class. So make sure you respond to claim your attendance. I will be, posting more of the attendance and grades on ELC in the coming days. Sorry that I've been kind of slow with that, but I'm sure you're anxious to see where you stand. So we still have, 10 more minutes, I guess. Well, does anyone have any more questions at this point? So I do want to say that this is pretty much what we have for class today. Again, I will send you an assignment to be completed before our class on Friday, which is going to be asking you to do the same interpolation, but for the files that you created. And again, if your summaries from the files you created didn't match mine, make sure they do before you start interpolating. If you need help with that, let me know by email. I can connect and we can troubleshoot that. Since we still have another 10 minutes, I just want to say that if anyone, like if you don't have anything else, if we can be done for today. I will stay around for the next 10 minutes, just in case someone has any questions about the mini project or maybe an assignment or whatever it is. If anyone has any questions, I will stay in the Zoom link for the next 10 minutes until our class time. And I'll be glad to help anyone with any questions. But if you don't have any questions and you don't want to stay around to hear what others may ask, you're free to go.